Welcome to the course module of Communication System Engineering. So in this video, we are going to learn about when this white noise process will be passed through a filter, then what will be the power spectral density function of output of this particular filter. So that we have to learn, and what will be the effect if such white noise processes will be filtered, then what will be the output power. So that we have to learn in this particular video. So let's begin this discussion. So let us say this. Suppose that we are having a noise process xt. Okay, so let us say that this white noise process is xt. So if we are having such white noise process xt whose power spectral density sxf is known, right? So here I have, just for the sake of completeness, I would like to mention that I'm considering this xt, which is a white and Gaussian noise process. Okay, so what does it mean by having a white noise process? I have already explained you in my previous lecture. So white noise process means it should have the flat power spectral density function. Okay, and Gaussian means it should have the probability density function, should be of Gaussian nature. Okay, it will be given by the Gaussian distribution. So that's why we are saying it is a white as well as the Gaussian process. So whenever such noise processes, if it is passed through a filter, okay, let us say the transfer function of this filter is HF, frequency response of this filter is HF. In that case, if you pass this particular noise process through the filter, and let us say this output noise process is represented by YT, then here we can see that this output noise process YT is having a certain power spectral density, which is denoted by SYF. So first thing that we have to understand that once this noise process is passed through the filter, the Gaussian nature of this output noise process will not change. Okay, so it will remain Gaussian, but normally it will not be a white process anymore. Okay, so it was at the input side, this xt was a white noise process, but at the output side it is no more white. Okay, because some of the noise component at certain frequencies has been filtered out by this particular filter, because whatever be the passband of this filter, that will allow only that portion of the noise to be passed, and the remaining portion will be filtered out by the filter. And therefore you have to remember this output noise process YT will remain Gaussian process, but not the white process. So normally after filtered, this type of noise is called as colored noise. Okay, so that you have to remember. And normally how to calculate this output power spectral density function. So this output power spectral density function is related to the input power spectral density function by this particular formula. Okay, so it is SYF is equals to SXF multiplied with the mod of HF square. Okay, so what is this mod of HF square? So this is the this HF denotes the frequency response of the filter. So we have to just take the mod of it and then we have to square it. Okay, so in this video, I will be explaining you first of all what is the noise equivalent bandwidth. Okay, we have to look at what is the noise equivalent bandwidth. To understand that, first of all, try to consider this particular picture. Okay, so let us suppose that we are having a white noise process, okay, whose PSD is given here in this picture. Here you can see that this is denoted by SXF, and this SXF is equals to N naught by 2. Okay, because it is a white noise process. So let us say that we are having a low pass filter. Okay, so here we can see that this is the low pass filter frequency response curve that we have. So once if you pass this particular noise process through this filter, okay, here we can see that it is a practical filter, low pass filter frequency response. Okay, so once you will pass it through this such filters, okay, in that point of time, if you wish to calculate what will be the total power available at the output of this filter, then obviously we have to first get this output power spectral density function SYF, and then this SYF has to be integrated over the frequency range of this particular filter, okay, over the pass band of this particular filter. So normally when it is low pass filter, if it is a practical low pass filter, we know that when frequency f tends to infinity, this frequency response h will become 0, right? And after a certain frequency, we know that there is a 3 dB bandwidth also. So here I'm just talking about if it is passed through the entire frequency range in which we are getting a certain pass band gain. In that case, this power that you can calculate is, we have to do this integration from minus infinity to plus infinity as YFDF, and then you can substitute for SYF, which is nothing but N naught by 2 multiplied with the mod of HF whole square. So we are just following this particular formula, and this way we can calculate the total power at the output of the filter. So now we have to try to understand that what is this equivalent noise bandwidth, okay, that we have to understand, right? So let us see this, what is noise equivalent bandwidth, right? So let us suppose that if we are passing this particular white noise process through such filters, and if this output of this filter is denoted by py, okay, here you can see this output of this filter is denoted by py, and if you perform this particular integration after calculating the SYF, we will be getting the exactly total power at the output of the low pass. So here what we are doing is, if you see, normally here we have this HF is actually not a flat spectrum. Okay, we don't have any flat frequency response as in the case of ideal low pass filter. So in the ideal low pass filter, we know that normally we are having a flat frequency response curve, and after a certain frequency, and there will be a stop band. Okay, so here we can see that we are having a stop band, right? So normally in the calculation of noise equivalent bandwidth, what we do is first we want to calculate what is the total power if this white noise process will be passed through such practical filter. First we have to calculate the py, and after that we have to consider such a ideal low pass filter. If you pass this white noise process again with such a ideal low pass filter, then again the total power content available at the output of the ideal low pass filter will be equal to the real low pass filter. Okay, so this is our real low pass filter. So let us say that if suppose if we design a filter like this, okay, if we design a filter like this, if this is the ideal low pass filter that we have made, suppose in that case, if you consider that, if we consider this type of filter here, we can see that we are actually neglecting these powers. Okay, here you can see that this range of frequencies has not been covered by this particular pass band, and again this portion is also not been covered by this particular pass band. Okay, again here you can see that this upper portion, okay, is also not being considered by this particular pass band. So obviously if you pass such noise through this type of filter with this much of gain, okay, in this particular pass band, okay, where the if you see this pass band, or you can say this will be the bandwidth of your ideal low pass filter, which is denoted by BNEQ. If you see, if you pass such noise process with this filter, the output power through this ideal filter, V output will be lesser than the PY. Okay, why it is lesser than the PY, that you have to understand, because you can see that this much of portion you are not included into this particular filter. Okay, again this portion will be neglected, and again this portion will also be not considered. Okay, and therefore we are actually getting the power that will be lesser than the PY, because we have to follow the same formula. Okay, again you have to understand that we have to follow the same formula. So now you just try to understand, if I increase the height of this filter, means we are actually increasing the gain of this ideal low pass filter, and I'm making it equal to H maximum, right? I'm just making it equals to H maximum. So here you can see that whatever be the power that we have lost in this section, actually it has to be compensated by this particular ideal low pass filter in this particular section. Here you can see that, okay? Because at this portion, if you see the real curve, okay, real filter curve, here you can see that the gain of your ideal low pass filter and real low pass filter both are same. But when you increase the frequency, here you can see that this gain of the real filter is increasing. But here the gain of your ideal low pass filter is greater than this particular gain of your real filter. And therefore, if you see whatever be the power that we have lost in this section, okay, in this section has to be compensated by this section. So accordingly, we have to choose this bandwidth of your ideal low pass filter so that the power lost in this particular section has to be compensated. So here you can see this definition of the noise equivalent bandwidth. It is the adjusted bandwidth of the rectangular filter such that the transmitted noise power through the rectangular filter and real filter will be equal. Okay, its power should be equal. So mathematically, the same thing has been done here. You can see that because Py through the real filter is actually defined by minus infinity to infinity SYF dF. It is equals to N naught by 2 integration over minus infinity to infinity mod of HF whole square dF. So we can define this noise equivalent bandwidth as this particular integration, okay, BNEQ, okay, it is defined as minus infinity to infinity mod of HF whole square dF divided by 2 H square maximum. Okay, so here you can see this B and EQ we have actually defined in the positive direction only, and because while calculating the power, total power by using the double-sided spectrum, we have to consider this band also. And therefore, I have just taken this factor 2 at the bottom. Otherwise, you can multiply B and EQ with a factor of 2, right? So the same thing we have done, and 2 multiplied with the H maximum square. This is the definition of your B and Q mathematical definition. And if you substitute for it, you will be able to show that this value, okay, if you consider what is the maximum value of HF, okay, here we can substitute for this particular value, okay, because it is a flat spectrum, we have to consider this maximum value of the ideal rectangular filter, that will be equals to H max. So here you can substitute for H max, so it will be becoming H square maximum, and this is going to be multiplied with this particular frequency, because this particular range of frequency in which we are performing the integration is minus infinity to infinity, but because this filter is exist only for let us say if this is representing you B and Q at this point, and then this will be representing you minus B and Q. So this particular integration will take place from minus B and Q, B and EQ to plus B and EQ. And then you will be getting this as 2 multiplied with the B and EQ multiplied with the H square maximum. So this way, basically, we are going to get this total power that will be equals to N naught multiplied with the noise equivalent bandwidth multiplied with the H max square. You remember that normally in the case of real filters, we need to have this characteristics curve. Okay, this HF or this HF should be known for all frequency components. But if you have the ideal filters, normally calculation would become easier, right? If we are having a equivalent ideal filters, then calculating the total output power of the noise will be easier. Okay, and that's why we are actually defining this noise equivalent bandwidth. Now here you can see that how to calculate the noise equivalent bandwidth for real filter. So let us consider that we are having a practical low pass filter. Okay, then how to calculate this noise equivalent bandwidth? So this is the characteristics curve of practical low pass filter. Okay, so its H maximum we have considered as 1, and then here we have this frequency component, right? Onto this axis we are having the frequency, and this is the our HF curve. Okay, so this is I have plotted the magnitude of your HF. So this will be your first order low pass filter circuit, and we have to apply the input from this 2 terminal, and then we have to take out the output from this 2 terminal. If you calculate the ratio of V output upon V input in Laplace domain, normally we get the its transfer function HF, right? So this HF is given by 1 upon 1 plus J 2 pi FRC. Okay, so we are just substituting R into C equals to tau. So this mod of HF you can calculate from this expression. So if you calculate this, you will be getting 1 upon root over 1 plus 4 pi square F square tau square, because if you calculate the mode, it will be square root under the square root, we have to calculate the square of your real part plus square of the imaginary part. And this way, if you substitute for into the formula of noise equivalent bandwidth BNEQ, you will find that this mod of HF square we have to substitute. So it is minus infinity to infinity mod of HF square df then divided by 2 h square maximum. So here you can see this h max square is equals to 1. Okay, because h max we have taken as 1, so it will be equals to 1. So after having that, we have to evaluate this particular integration, right? First, we have to evaluate this integration, and then we have to substitute into this particular formula. And that integration I have done this side. You can see if you substitute, because it is this curve is symmetrical around symmetrical curve. Okay, onto the frequency scale, what we can do is you can rewrite this expression as multiplying a factor of 2 by using the property of your integration, right? This integration can go from 0 to infinity. Okay, so here we have to just make certain substitution, right? I have just done this substitution, u equals 2 pi f tau. You can substitute it. It is very simple to do. And then you can calculate this df will be equals to du upon 2 pi tau. Then again, you can see that this term will be a constant. It will come out of this integration, and then we are going to get this du upon 1 plus u square. So that will be having its integration will be equals to tan inverse u. And if you substitute that limit, you will be getting pi by 2. So ultimately, if you do this integration, we are going to get this equals to 1 upon 2 tau. So the same thing I have substituted over here. You can see noise equivalent bandwidth will be equals to 1 upon 2 tau divided by 2 into 1, because h square max is equals to 1, right? So here you can see, you can substitute for tau, you will be getting 1 upon 4 RC, right? So we have got this result 1 divided by 4 RC. So now you can calculate, if you pass the white noise process through such real filters, then you can calculate what will be the total power at the output of such filter. Okay, so that will be given by is py equals to n naught by 2 minus infinity to infinity mod of hf square into df, right? So that if you substitute for, obviously, you will be able to show that this value is equals to py equals to n naught upon 4 RC. So I have directly used this particular formula. Okay, you can see this is py is equals to n naught multiplied with B and Q noise equivalent bandwidth multiplied with the h square maximum. So here you can see h square maximum is 1 and n naught. Then we have to put this noise equivalent bandwidth. So here we can see that this noise equivalent bandwidth that we have calculated is 1 upon 4 RC. So that's why it has become n naught upon 4 RC. And now you can further see, if we take this double-sided power spectral density of white noise, and if you pass it through the ideal low-pass filter, let us say we are having this ideal low-pass filter. If you pass it through such particular filters, which is actually the mathematical definition of such ideal filters is given by this particular expression. Here you can see hf equals to 1 for the mod f less than equals to b, otherwise it will be 0. Okay, so again, we have to follow the same formula of total power at the output of this particular filter. You will find that obviously you can substitute for this particular values of mod of hf whole square. You'll be getting 1. Okay, and then you have to just do the integration from minus b to plus b. So you'll be getting 2b, right? So n naught by 2 multiplied with the 2b, you will be getting py equals to n naught into b. Similarly, if this white noise process will be passed through ideal band pass filter. Okay, let us say this type of noise is passed through the ideal band pass filter. Then here we can see that only for this particular portion, this noise will be passed, right? Only for this particular frequency range. Because at the other ranges, when you multiply these two signals, this value will be cancelled out. This value will become zero, okay? Because there is no passband of the filter at this range, but only this is the passband of the filter, and therefore the output that we are going to get is only for this particular frequency range. So again, if you do the same thing, right, here we have to do the, again, you have to perform the integration. And if you perform the integration into this particular frequency range, just make it twice and then n naught by 2 0 to infinity. And while substituting for the band pass, you have to substitute these two frequency points. Okay, we have to just substitute these two frequency points so that you can find it out easily. And this py that we are going to get is 2 into n naught into w. So this will be the result of passing the white noise process through the band pass filter. You please remember this point, okay? So this will be the output noise power, right? So here one thing that you have to remember, if we are having a double-sided power spectral density function, and if you are having an ideal low pass filter or a band pass filter, in that case is normally the output power can be given by this particular equation. Okay, what is this equation is? Output power is equals to twice of double-sided PSD of white noise multiplied with the bandwidth of the filter. Okay, so here you can see that in both the cases, if you use the same formula, double-sided spectrum PSD of the white noise, so it is 2 into n naught by 2 multiplied with the bandwidth of the filter. So bandwidth of the filter is B, right? The bandwidth of the filter is B. So it is 2 into n naught by 2 multiplied with B. So 2 will be cancelled out. We will be getting n naught B. Similarly, again, here you can see that if you substitute the same thing, it is 2 multiplied with n naught by 2. And then the bandwidth of the filter is 2W, right? So 2 and 2 will be cancelled out. We are going to get 2NW, 2NW, right? So this way you can calculate the power at the output of the filter. So I hope you must have understood how to calculate the power when the power of your white noise when it is passed through the ideal low pass filter or ideal band pass filter or any real filter by using the concept of noise equivalent bandwidths. So if you have any further doubt, then let me know with your comments. And thank you for watching this video, and stay connected with this channel for more updates. Thank you.